Okay, good evening, good afternoon, good morning. Thank you very much for joining us. Welcome to day 5 of the workshop on AI and HPC technology in semiconductor manufacturing. My name is Pradeep. I'm from KLA, and I'm co-organizing this workshop with Rupesh Nasre from IIT Madras. Okay, good evening, good afternoon, good morning. Thank you very much. Sorry about that double voice. So this workshop is organized by KLA and IIT Madras, the Nodal Center for Training in AI and HPC under the National Supercomputing Mission of India. A brief look at the workshop agenda again. So this workshop is laid out as a series of 5 talks, with Chris kicking it off with an overview of the problem space. The next talk gave a high-level idea of the several AI challenges in adopting AI technology into manufacturing. Steve spoke about some infrastructure-related components that we build in the fab using the various AI models. Mark's talk yesterday spoke in detail about a very subtle but a very intelligent technique of how to minimize copy overheads when sharing GPUs in a box. Is a very important problem to deal with. And today's talk will focus on running AI inference on the CPUs. So the 4 talks that have been completed from Monday, the slides are already available on the workshop website, and recordings are available on YouTube. You can access the recordings through the workshop website. And today's talk will focus on running AI inference on the CPUs. While we welcome everyone to attend these talks, the ideal audience for which we had prepared these talks was for either a senior, that's a 4th year in engineering, or a 1st year MS level student in computer science, electrical engineering, or the sciences. If you are less experienced, we definitely recommend that you listen to us and you come back and listen to us once you've absorbed some key concepts in foundational technologies such as machine learning algorithms, distributed computing, semiconductor device modeling, and GPU programming. So once you've gotten a grasp of those fundamentals, please come back and see the videos, so that I think that way you'll grasp a lot more than what you'd have gotten the first time around. And finally, we realized that there's a lot of terminology that we use in our slides. So we have tried to make sure that we add a glossary of terms to our presentation material to ensure that you can follow the material with the relevant terminology as and when required. Before we kick the talk off today, a relook at some of the workshop logistics that we've been using. It's the same link to join the Zoom webinars. Again, we are inching close to 1,500 attendees on Zoom and more than 200 live stream viewers on YouTube. The YouTube links are per session. If possible, please join on Zoom, because you get the full experience with question and answers. You can view the live stream on YouTube as a backup. For post-session viewing, of course, please use the YouTube links, because they will be available later as well. Each session has been following a similar pattern, same routine today. First, set up an introduction up to 10 minutes. The talks have been pre-recorded by the speakers to make sure that we don't have connectivity issues, a maximum of 40 minutes for the talk. And then in the end, we'll reserve at least 10 minutes for Q&A. Please use the Q&A window at any time to post your questions. Since the talks are pre-recorded, the speaker is available to answer questions live, and so are all the panelists of all the talks. The speaker will select a few questions that will be answered live in Q&A. Finally, if you're interested in a certificate of participation, you should have already by now attended 4 of the talks for more than 80% of the time. If you are joining on Zoom, the attendance is automatic. By virtue of you signing in, you've already registered your attendance. There's nothing more to do. If you're signing on YouTube, please fill the Google form, which I will post as a pinned comment after this introduction. If you have joined on Zoom or YouTube, please make sure that your name and email address are the same, because that's is the same as what you'd use to register, because that's the way that we'll be sending out the certificates. Now, since today is the last day for the talks, we will start processing your certificates after this. We have a lot of processing to do, because we've had more than 2,000 attendees every day. So it'll probably take 2 to 3 weeks for you to get your e-certificates. So please stay tuned and wait to hear from us. Based on experience over the last few days, we've put together some housekeeping rules to make sure that our channels on Zoom and YouTube are clean. Okay, first and foremost, please exercise judgment in Zoom question and answers and YouTube comments to keep them relevant. If possible, please check the answered questions on Zoom before you post a new question, because chances are the same question has been asked by several others before. Please avoid greetings in channels. We've had several attendees through the days, these channels can fill up really fast, right? So while we are very excited to have you on board and we are happy to greet you, please avoid posting those on the channels. If you're interested in opportunities at KLA, please reach out separately. Don't put a message in Q&A. There are enough pointers on how to reach out to us. Please use those. If you have audio or video issues, please check your volume or move between. If you're having issues in Zoom, go to YouTube. If you're having issues in YouTube, come back to Zoom, right? From our side, we're doing the best we can. We're uploading very high quality video and audio. So it's up to them to deliver it to you, but I apologize on their behalf if it doesn't do a good job, but hopefully moving helps. Again, to reiterate on attendance is automated via Zoom and it's via Google Form on YouTube. Okay, and if your names don't match on Zoom, please go to Google, go to YouTube and fill the form. There's no need to do both. Just one of them is sufficient. And again, to reiterate, please reserve Q&A and comments for relevant questions for the speakers and the panel. That way, if you form your questions well, it will be most engaging for the rest of the audience and even for you to get a good answer. With that, let's get ready for the landing. This is the final talk of the session. And to introduce the talk and the speaker, I will let Rupesh do the honors today. Rupesh?
Thanks, Pradeep. So welcome everyone. And the best talk of the series is kept for the end. And it's my pleasure to introduce Pradeep for this talk. He is going to talk to us about AI inference on CPUs. Dr. Pradeep Ramachandran is the director and head of KLA's AI Advanced Computing Labs. And prior to joining KLA, he has worked in multiple companies. And primarily his focus has been on hardware chip design on CPUs and video compression software for broadcast, streaming, etc. And he has been juggling around with getting the best out of the hardware software co-design. Pradeep holds BTech from CSE, IIT Madras, and MS and PhD from UIUC. Pradeep has also been a colleague at the department where he was an adjunct faculty in our department for 4 years. This talk on AI inference on CPUs is going to be primarily also focused on the hardware and software interface. If you have some background on, let's say, computer architecture, electronics, if you have heard of SIMD, vector instructions, this is something which you will probably enjoy more. But of course, everybody has something to take away from this talk. So without further delay, let's welcome Pradeep Ramachandran.
Thank you very much for the very warm introduction. It is indeed an honor to be given the opportunity to take this wagon that has been steered by stalwart speakers before me. I will certainly do my best to do justice to steer it home well. Thank you very much, KLA and IIT Madras, for giving me this opportunity. Before I dive into my talk, I do want to put one disclaimer out. Most of the material in this talk is based on publicly available content, and all of it has references in the slides themselves. I've tried to organize this more like a tutorial than a description of the technology that KLA uses. And of course, all opinions expressed here are mine and don't represent KLA's opinion in any which way. Now, with that out of the way, let's dive into the talk. So I titled this talk Running AI Inference on CPUs. And the first question that naturally comes to anybody is, with so much talk going on about GPUs or graphics units and accelerators, why is it even important for you to run inference on the CPU? First and primary reason, because it's there. Whether we like it or not, every system today, especially in the HPC domain, has a powerful CPU that hosts system and legacy applications. So there already exists a fairly powerful CPU on which you potentially can run inference. Now, secondly, while accelerators are the new kid in the block, even GPUs, it is not necessary that every system has such an accelerator available for inference. In fact, it's possible that in some scenarios, you might not even know the scenario in which or the system in which a deployment is going to happen.
So for example, whether you're going to run it on the edge, whether you're going to run it on the cloud, you might not even know when you build the application. Now, if that be the case, you are guaranteed that there will be a CPU at all given cases. And therefore, figuring out how to run AI inference optimally on the CPUs is very important. Thirdly, and arguably the most important reason, is that the data for inference is actually already available on CPU access memory. So there's actually no need for data movement. Now, this is a subtle point, but a very important point. And let me try to illustrate this with some data. So what we have here is a simple cartoon that actually shows you what a CPU looks like, its connected system memory, and then there's a GPU in the diagram and its connected GPU memory. And there's a little connection that connects the CPU and a GPU. So now if your GPU actually has to work on data, it needs to be moved from the system memory by the CPU into the GPU, into the GPU's memory, such that the GPU can then operate on it. And this connection is typically through some system level component like PCIe or CXL. So now let's look at some typical bandwidths at which these various interfaces operate. So the data on the right side shows you some typical interfaces, what I believe are modern connections, which are typical in HPC systems of today. System memory, which is this orange block here, is typically like an 8-channel DDR4 3200. Of course, significantly more powerful than what you have on your laptop, but this is a high performance cluster. So that has a theoretical bandwidth of about 200 gigabytes per second. So this connection operates at about 200 gigabytes per second. It's pretty good. However, if you look at the GPU memory connection, which is this purple connection here, that's typically now a HBM2, a high bandwidth memory 2, and that's north of 1500 gigaflops, gigabytes per second, which is significantly faster than what your system memory gives you to the CPU. So obviously it makes more sense to put your data here and then to operate it on the GPU. However, to bring it from here to here, you need to go through this connection, which is either in today's systems, a typical Gen 4 PCIe by 16 lane, which is a 32 gigabyte per second connection, or there are more advanced connections like the NVLink, which is used by the NVIDIA GPUs, or which is used in the XXM2 connectors that NVIDIA GPUs have today, which is closer to like a 300 gigabytes per second. So now, as you can see, there is actually a big gap between the speeds at which these connections operate to the speeds at which you actually are able to use the data. So now if you have to move the data from here to here, you are going to get bottlenecked by this connection, which is running typically at much slower speeds. Therefore, it behooves you to first try and run AI inference on the CPU itself, and then, and only when it does not make sense performance-wise to run this on the GPU, to actually root on the GPU. Now, before we talk about how one can actually run AI inference on the CPU, let's try to understand some of the typical compute and data patterns of AI workloads. Now, it's very important to understand these patterns because it is an understanding of these patterns that has resulted in several innovations in both CPU and GPU, which our application writers are able to exploit. So the picture on the left shows you a typical convolutional neural network. It shows you the dense layers of the convolutional neural network. So you can see here a simple network that has an input layer shown in blue, a couple of hidden layers with different number of neurons, and output layers shown in red, and then an activation function that is applied on top of the output. Now, mathematically represented, this actually is you take your inputs, you multiply them by their weights, and then you add all of them, showed here by the sigma, and then you apply a bias factor to that, on top of which you apply an activation function. So again, multiply, add a bias, and then apply an activation function on top of that. So this is a typical layer of the dense layers. Sorry, typical operation of the dense layers. Now, if you consider the typical operation of the convolution layers, on the other hand, this is what a convolution operation typically looks like. You have a kernel here shown in a 3x3 matrix. You take the kernel and you apply the kernel on an input. So you basically project the same sets of pixels of size 3x3 on the input, and you dot product element wise and you add all of them. So you multiply and then you accumulate to get the final output, and so on and so forth. So there are a couple of key observations about compute patterns that you observe are actually very useful for us to realize. Firstly, multiplication followed by addition or reduction is a common operation. So you saw that here it's multiplication followed by addition. Similarly, here you dot product multiply and then you add. So it's a very common operation. Secondly, most operations are actually repeated across data elements and there's very little scalar operations between them. What do I mean by that? If you actually take this convolution, this kernel is first applied on this 3 by 3 and then applied on the next 3 by 3, shifted by 1 pixel, next by the next 3 by 3 and so on and so forth. Now, the operation of one 3 by 3 block is completely independent of the operation of the next 3 by 3 block, but it's the same operation. So there is a notion by which you can have parallel data, but the same operation. That's the kind of compute that you actually see. Let's make some key observations about the data patterns. That's also very interesting, right? So the first thing that you observe is that the outputs of one layer serves as inputs to the next, but the inputs are not reused. That is, if you take this network, your hidden layer 2 uses the outputs of hidden layer 1, but have no connections from the input layer, which basically means that once hidden layer 1 is done, you don't need input layer hanging around. You can throw it out. Secondly, when you have multiple instances of inference running on the same system, only the weights are reused across the instances. There's no other information that's getting shared. What do I mean by that, right? So if you have, let's say, this network and you have the same network instantiated again, you're going to be running these networks on completely independent data. So there is no need for you to share any information between them except for the weights. This is primarily during inference because the weights don't change either. Now, based on this, CPUs have actually been designed to exploit these compute patterns. And let's look at the various design elements that have been introduced into CPUs based on these compute patterns. So let's start from the first row here. So the first workload pattern that we observed was that multiplication followed by addition was a common phenomenon. The CPU support for this was that they added a natively supported fused multiply add as a single instruction in the instruction set architecture or the ISA. What is the advantage of this? This meant that to do multiply and add, you did not want to do a second instruction. You just issued a single instruction, and that actually significantly limited the bottlenecks in the front end of the CPU, which is the fetch and decode cycle, because fewer instructions are flying through. That gave significant performance. The second observation we had was that most operations are repeated across several data elements. So the ways that the CPUs are starting to exploit this is that the width of the existing vector units, which are already data parallel execution units for multimedia workloads, has been increased further to support matrix-like operations. And that significantly increases the throughput for the AI loads. If that sentence did not make too much sense, that's okay. So hold on to your thoughts. We're going to dwell about this in a fair bit of detail in this talk. The third piece that is also increasing in pattern that we're starting to observe is that while the amount of scalar operations have been traditionally very limited, there is an increased use of limited scalar operations amidst the parallel operations in the networks. So one of the supports that the CPU is actually adding is to actually be able to do thread ganging, where you don't do embarrassingly parallel execution, but you take a few threads of the CPU or a few cores of the CPU, focus them on one execution or one inference execution, take a few other threads, run a second inference session, and so on. So the advantage of this is that if you have any single threaded performance of the CPU, which means that you cannot do the full parallelism, you still get the advantage of getting very good throughput because of the single threaded performance of the CPUs, and that helps significantly improve inference throughput. For the rest of this talk, I will be focusing on these three elements of the compute patterns and how CPUs have been designed to exploit it. I will not focus on the data patterns because that can actually be a complete independent talk by itself overall. So let's talk a little bit about inference with CPU vector units. So the pictures on the left side actually show the kind of data pattern that we are trying to exploit with these vector units. So the first data pattern is called SISD, or single instruction, single data, where each instruction operates on a piece of data and generates its results. So you have A0 plus B0 gives C0, then you issue A0 plus A1 plus B1 gives C1, and so on. Now, the kind of data kind of a compute pattern where you have a single instruction and multiple data coming in to generate multiple results is called SIMD, or single instruction multiple data, where you have multiple data elements coming in, but just one instruction, just one add, and then suddenly all your outputs are computed using the same instruction, arguably in much fewer cycles than it would take you to do these 4 adds. This is what vector units have enabled us for generations. So let's look at how the vector units of the CPU have been designed and how we can leverage them for AI inference. But we'll start with the basics, right? We'll start with the basics of how vector units started and then move on to more practical implementations. The basic idea for vectors is very straightforward. The idea is that you read a set of data elements into vector registers, you operate on those registers, and you disperse them back to memory. So the picture on the right here shows you a scalar register file that has multiple registers, and a vector register file, which for each vector register is a bunch of scalar registers. So you load and store your vector register file much like you do your scalar register file, and you're able to operate on it. Now, in vector architectures, the vector register file is completely visible to the compiler. So there's no notion of a separated virtual and physical register mapping, which is the kind of stuff that a superscalar execution engine does for scalar registers. In vectors, your compiler completely sees your vector register file and can use schedules to hide memory latency and to leverage memory bandwidth significantly. Let me show this with an example. So the code here is a simple DAXP function. DAXP is a double precision AX plus BY. So that's why you have a RY, you're trying to compute RY equals A times RX plus RY, where A, RX, and RY are memory. In your vector, in a vector ISA, there's a simplified MIPS ISA extended to vector. You'll actually see that you can do this with very few instructions, because for each vector operation, you're loading tens or hundreds or tens of registers in one shot. So let's quickly walk through the code. Your code starts out with doing a load of a scalar, which is A. You load it into a scalar register F0. Then you do a vector add, where you load from memory address Rx into vector register V1. So all the elements of the vector get filled. So you're not pulling in just 64 bits, but you're pulling in arguably much more than 64 bits. Then you do a multiply of a vector and a scalar, mul vs.d. .d stands for double. So basically you're doing A times Rx in this. You have A times Rx stored in V2. Then you do a vector load of Ry into V3. Remember, that's the second operand. And then you do an add of two vectors, VV, vector and vector, to get the output in V4. And then you store the output in V4. Now, this is just 6 simple instructions, right? Now, if you have to do this in scalar, for each of the elements of V1, we'll have to write a load, a multiply, another load, a add, a store, and go on and so on, go on. So this is really the beauty of vector instructions, right? It makes your code so much simpler. However, one key observation that people had was that having a vector in a program to be exactly the width of the vector register file was very difficult. Your vector register file could be, 64 or 32 bit per element, and then you can have 8 or 16 registers. But it is very difficult to handle. It is very difficult to find parallelism like that, right? You in fact could have vectors that were typically either longer or shorter. So there were 2 additions that were done in order to support vectors that were either longer or shorter than the default width of the vector register file. The first was to support variable length registers by exposing 2 registers called MVL, that stands for the maximum vector length, MVL, and the current vector length register is stored in a register called VLR. So the idea basically here is that your vector of length VLR is composed of multiple smaller vectors of length MVL and then a short tail in the end. So here, each MVL sized vector can be operated on in one iteration. It's very easy going that way. And in the end that you have the tail, you have the remainder of VLR mod MVL, and that's handled in the last iteration. Now, the interesting thing here is that the tail has fewer elements than the entire width of the vector register file. So you need a way to be able to handle that. How do you do that? The way that vector architectures do it is they introduce what's called a mask register that enables disabling some elements of the vector during operation. And with that, you're actually able to get a full vector, which is longer than MVL, be operated upon using either for a DAXP loop or for any other kind of loop. Now, in theory, this was actually brilliant. And in fact, we had the Cray-1 system implementing a pure vector cell architecture. But the problem was that in reality, this machine was way too wide. very few practical applications actually had this much vector parallelism in them to be able to use. So the world actually turned to a more practical implementation of the vector architecture, which is called SIMD. So there were two key observations again that were made that led to the practical adaptations of the vector architectures. First, up to about a decade ago, the prevalent data parallel applications that were, the mainstream were media workloads. I mean, even today, sorry, don't get me wrong, but media workloads continue to be very important because you, for example, will not be able to see this webinar if media workloads did not exist. But the main data parallel applications of this decade has become AI applications, right? But media workloads have been around for decades, and they have actually driven some of the technology that's gone into CPUs for many years. Now, these media workloads, when one observed them, it was observed that they operated on data that was shorter than 64 bits. It was either 8 bits or 16 bits typically, and that was dictated by the width of the pixel sensors that are available in cameras. And even today, to be honest, there are very few cameras that go up to 16 bits. So providing a vector register, which was 64 bits per element, and then NVL number of registers was not that useful. It made more sense to be able to break that NVL times 64 bits into smaller chunks of 8 bits or 16 bits. And that's really what SIMD does. So CPUs today actually provide vector units that operate on what are called configurable register files. So you basically have a dedicated integer and floating point vector register file, but it can be configured for various vector lengths. For example, the integer register file can be configured to have n 8-bit registers, or n by 2 16-bit registers, or n by 4 32-bit registers, and so on. The FP file supported single or double precision floating point, and you could have either k 32-bit or k by 2 64-bit registers. And the ISA was also extended to support dedicated instructions for different vector widths. And so, for example, the AVX instruction set actually has a V add PD for double precision floating point registers and a V add PS to support single precision floating point registers. These implementations where the CPU supported vector units of configurable register files is called SIMD or SIMD vector unit, standing for single instruction multiple data. And this has been implemented by CPUs across x86, across ARM, across Power for the last several decades. The latest generation of them, of course, being AVX 512 that the Intel Xeon scalable processors implemented, but it's been supported by Power for generations in the Neon architecture for ARM and so on and so forth. Now let's look at a case study of how video encoders have been implemented leveraging these vector units to get significant performance gains. Now video encoders are highly data parallel applications and they can leverage vector units for SIMD parallelism. The reason is because pixels that are represented as 8-bit or 16-bit integers, they have integer and floating point operations happening on them, right? Sum of absolute differences between two pictures or mean square error between two pictures, which are completely parallel. Every pixel, you take the corresponding pixel between two images and you do the same operation. So the same operation, multiple data, SIMD, very, very natural fit. So there was a study done by codec experts at Multicoreware in collaboration with Intel, where they had shown how two popular open source video codecs, X264 and X265, can leverage SIMD parallelism to get significant gains. The graph here on the left side shows the relative speed of the two applications, X264 and X265, when they leverage AVX2 SIMD on a particular Intel Xeon CPU when compared to running straight line C code. So if you look at it, X264 gains something of the order of 2.5x and X265 gains something of the order of 5.5x, right? So this is 5.5 times faster with SIMD when compared to straight line C code. And remember that this is speed up actually on a single threaded application. Parallelism, that is when you run multiple threads for the application, is a speed up of X factor on top of this. Every thread gets this much faster. So that's really the power of SIMD, right? So we can see right there off the bat, you're getting something between 2 to 5x speed up on a real world application that is very popular today. The second graph on the right side shows you the generational improvement of moving from AVX2 to AVX512. There are different presets that are shown here. You can read the paper for more details, but this last preset, very slow, is a popular preset that's used for high quality video streaming. Now, you may think that 10% of speed up is pretty small, but considering that these codecs actually are used by some of the largest OTT providers in the world that stream to millions of hours of content to millions of televisions and devices over the world, even this small meager 10% can result in saving millions, if not billions of dollars. So it's really, a great gain that one can achieve by leveraging SIMD. And with every generation, the gain is also growing. So it actually makes sense for you to start intercepting every generation. Now, the astute eye here may have noticed that with this particular preset, the very fast preset, there's actually a slight slowdown. Hold on to the thought. We'll come back to that in a little bit. So now that there are vector units that are available in the CPUs that have already been designed, developed, and being used for media workloads, it is a natural extension for AI inference where the AI workloads that actually use matrix operations. I'm just showing you an example here where a convolution is a very typical matrix operation. These modern CPUs are actually adding matrix units in addition to vector units to enable AI inference. Recently, Intel released the advanced matrix extensions focused on AI loads as part of their Sapphire Core releases. And in these architectures, the change is that what used to be a register file of a vector is now a matrix. It's a tile. So for example, a 2D tile of registers contains 8 registers of 1 kilo bits each. So it's 1024 bits. It's a pretty big register. And then there are dedicated instructions like the tmul instruction, which is a tiled multiply, matrix multiply add, which is done on 2 tiles. So you have a tile A and a tile B, and you do a matrix multiply to them, and then you accumulate it into a tile C, all of it done with a single instruction. So that's a lot of SIMD, a lot of data running in parallel with a single instruction called tmul. And a consequence of this is that the throughput, when you leverage something like an AMX instruction of tmul, goes up 8x per op, per cycle, per core. So the more cores you have, the more gains you get. So this is really good, right? So you can actually get 8x throughput by just porting your applications from using AVX512 to AMX. So that sounds really good, but with vector, the experience suggests that there are a few hidden skeletons in the closet that you got to be careful about. Let's talk about a few of them. The devil in vectors is indeed in the detail. The bright side of vector and matrix implementations is great, and it gives fantastic throughput. But a big downside is that they take clock speed away. So the table on the right side shows a measurement done by AnandTech on Cannon Lake processors, where they were actually showing what the various frequencies that the CPU was able to sustain in different modes. You'll see that the base frequency is 2.2 gigahertz. If you're running an application that's using only a single core, you can actually turbo up to 3.2 because other cores are shutting down. If you run on 2 cores, you can go up to 3.1. If you run with AVX2, you're back to the base frequency because you can no longer turbo because you need that much power. But the interesting thing is that if you move from AVX2 to AVX512, you can't even get to the base frequency. Right? You're only able to sustain a 1.8 gigahertz or a 20% lower frequency when you start using the newer generation, higher throughput AVX512 units. Now, it's not all grim that you're going to suddenly lose 20% performance, because if you ported code from AVX2 to AVX512, you are going to get your 2x throughput. So your 20% reduction in CPU clock frequency is significantly offset by the fact that you got a 2x throughput improvement. However, life is rarely so fair. It's very rarely the case that you will be able to port all your workloads from AVX2 to AVX512, or that all of them fit in AVX2 to begin with. And so this reduction in clock speed could be a significant impact to your application. So you got to be careful. The devil is indeed in the detail. Secondly, while it's great to adopt the new generation, automatic code generation is not yet practical. And that plays a significant impact to engineers like us. Because what this means is that for every new generation, you literally have to take on and rewrite all the kernels in the new generation. And to overcome the frequency hit of things like this, you need to make sure that you write enough kernels. So the graph that I show on the left side is again from the paper from Multicore and Intel, where they demonstrate that to get the kind of gains that they had shown, they had to rewrite, hundreds of kernels in a fairly complex video coding application. It's a lot of work, right? So I have to be honest in that writing vector implementations isn't necessarily the sexiest thing to work on, right? Doing uh, new ISA advancements might be even more sexy to work on, but it is indeed the biggest bang for the buck. In fact, once an application starts functioning, the first thing that any practical application goes through is performance optimization using vectorization. So if you are a student who's looking to enter device parallelism or to enter performance optimization, I recommend that you start here. It is very easy to learn, and the return that you get on performance for the amount of time that you invest is actually tremendous. You can get really good gains, especially when you start with things like AVX2, because the clock frequency dip is not there. You start getting performance gains right off the bat. Now we are observing a recent trend, which is, kind of turning a few heads. So I thought it would be only appropriate for me to bring that recent trend up here. So in a recent article by David Patterson, the father of computer architecture, I'm sure most of you have gone through the computer architecture course, have studied his textbook, and on Andrew Waterman, group chair of Privileged Architecture Group at RISC-V, they observed that while SIMD is a huge success, it has significantly complicated the ISA. So they actually analyzed the instruction set for the IA32 instructions, which is the x86 instruction set for 32-bit architectures. And they observed that the number of instructions has grown from 80 in 1978 to about 1,400, and that in 2020, and largely due to SIMD. And so what this means is that your decoder, your front end, right, your fetch, your decode, needs to now account for the fact that you could be using one among 1,400 instructions, making them significantly more complex. And the job of the user, it is either the application writer or the compiler, even more complex because they now have to figure out which instruction out of 1,400 do I pick. It's easier to pick one out of 80. Picking the right one out of 1,400 becomes so much more harder. So what RISC-V has recently proposed is that they are proposing that they go back to a vector-like ISA that uses VLR and MLR, which is the vector length register and the maximum length register. So they're saying that what the compiler and the user sees will be registers of 64-bit width, and operating on them as lower width registers will be fully handled by the hardware. So the compiler or the the compiler or the programmer does not have to worry about that. What this does is it significantly simplifies the ISA and the amount of overhead required when you have to run code. So if you look at this table here, it actually shows you that to write a simple loop, your static instructions, which is again the number of instructions that a programmer or a compiler has to generate, reduces from 29 with AVX2 to 13 for RISC-V. That's half the size. So it's significantly simpler to write. And similarly, when it dynamically executes, the number of instructions that are in the flight reduces from 1,500 for AVX2 to 163 for RISC-V. Again, significantly simpler, which should theoretically translate to performance. However, with vectors, the proof of the pudding is always when it runs, because the devil, as I've already mentioned before, is in the detail. So we are curious to see how this translates to performance. And I would be really, it would be amazing to be able to simplify the ISA to a point that it makes the programmer's life a lot easier to write these applications. Now that we understand vector units very well, their lineage and practical implementations, let's look at a few other advancements based on our observation of compute patterns that actually aid inference. So the picture on the left side is one of a upcoming CPU, a Xeon CPU from Intel, codenamed Sapphire Rapids. It implements many advancements that we talked about earlier. There's an AMX unit. You can see there's an AMX thingy here. There's a few units called FMA. There's a fuse multiply add units. And some of the other stuff that I'm going to talk about here are supposed to be in there as well. It's a evolutionary jump to CPU performance, and the whole industry is actually waiting to see what kind of improvements it brings to AI inference, and we are waiting as well. So let's talk about a couple of extensions to the ISA with the focus of aiding inference. Like I mentioned, since multiply and add are common operations, most CPUs today actually support fused multiply add instructions at a very low latency. Initially, again, they came for media workloads, and you can see a few examples of these here, right? Basically, you're trying to do A times B plus C, and different instructions support either you do it as plus A or minus A, and you do plus B or minus C, and so on and so forth. Additionally, another extension to the ISA has been that there's an observation that multiple instructions together are used commonly for AI inference. So there are extensions like the Intel VNNI where specific AI focused instructions are fused together, and then you generate a single VNNI instruction, which again significantly reduces the amount of throughput that your front end has to deal with. And these kind of advancements can be leveraged by the compilers during backend code generation and can also be written during intrinsics or assembly language programming. So these again significantly aid inference. Now, the other piece that is recent development in the CPU world is that there's an observation that especially when you have CPUs that have several cores, which is very typical in a HPC system, you might have lightweight inference that you want to do, which don't need all those cores. For example, think of a bank authentication scenario. Think of a web query example. Now, of course, AI has penetrated so much that all of these workloads also use AI today, but those inferences are very light. And those inferences might require, especially if they're time series bound, they may have more serial compute than your traditional convolutions. So for this, what CPUs today provide is an ability to group multiple cores together and to run multiple sessions of inference. So the picture here actually shows you several inference sessions running on the same CPU at the same time. Now, the multiple inference sessions offer several advantages, right? So firstly, you have reduced your synchronization overhead because you don't have to wait for all the cores to be ready to synchronize. And you're improved if you're able to figure out a way by which the working set of these groups of threads fits in the L2, you actually are working out of the L2 and you don't even need to go to the DRAM. So you actually could get significantly better performance coming out of this. Now, this idea is not new, right? This idea is similar to the idea of MPS or multiprocess service with CUDA that was proposed by NVIDIA for its GPUs. But this is something that on the CPU side that you can gain a lot from, because especially if you have a lot of single-threaded application or a single-threaded dependency on the workload, doing this kind of ganging could be really beneficial. Now, one thing we should always remember is that CPU is not new. Right? So techniques that are being used for other accelerators are also applicable for the CPUs. For example, operating on models with reduced precision and inference is something that can also be used on the CPU side to improve performance. In fact, CPUs today natively support block 416 and a lower precision inference using Witts vector units. And these lower precision models actually double throughput very easily. Now, there is an impact to model accuracy, but there's lots of research going on how to limit that. So there's always benefit of doing that. Secondly, fusing kernels to limit the data movement between caches and memory is another opportunity where that is used by accelerators to improve performance, and those are also applicable for the CPU. Now, this particular piece, being able to do this on a CPU, is very interesting for the compiler people because this actually is a great candidate for auto generation, and the compiler community is very excited about it. And there are other learnings from the GPUs that can also be observed. Now, having seen what the CPUs have to offer, I bring back a slide that Chris had showed at day one, which showed us that for the kind of loads that is used by the KLA systems, GPUs today offer a performance benefit of anywhere between 2x to 15x. However, we are hopeful that with new technologies like AMX, the gap between CPU and GPU in terms of performance hopefully narrows down. And since decisions are made not just based on performance, we hope that this brings CPUs back into contention for inferencing, at least in certain use cases, and especially in the HPC domain. So we've been talking a lot about CPUs and how to run inference on the CPUs, but there are two very incumbent revolutions for AI inference that we are looking at. And as the world moves forward, I'm very excited about these two revolutions, which I think is, going to really pave the way for how inference runs in the future. Firstly, there's a lot of work going on in what I call the hardware revolution of trying to bring CPUs and accelerators closer together. CPUs and accelerators, I believe, will continue to coexist, right? So it's important that you bring them closer and take care of the bottleneck of data movement. So there's a lot of work that we see happening in the domains of newer generation PCIe connectors, there's CXL, there's NVLink, and even cache coherent accelerators. That's a very exciting opportunity because that limits the overhead of data movement, which, as Mark spoke about yesterday, is a very big bottleneck. Secondly, there's a software revolution going on where there's a lot of focus on auto-generated code. Now, in the practical world, what actually ends up happening is that deployed workloads use a lot of hand-tuned kernels. This could be written in CUDA, in SYCL, or whatever. And every new hardware generation, as I've shown you with the AVX2 and AVX512 implementation, requires re-implementing these, which is highly impractical. You're not going to spend hundreds of man-years worth of effort to do this for every new generation. So if you could auto-generate HPC code, and if you could auto-generate performant HPC code, it makes the case for it to become very attractive. And so there's a lot of communities actually working on this, several in the open source and some in the closed source domain, that has us very excited. So we are hopeful that these revolutions enable us to scale AI inference in the long term without having to do too much hand coding and hand holding. Now let's take this home by concluding the talk. I believe that CPUs can be considered the first option to be used for inference. Now accelerators, while they're performant, it's not default yet. And there are many key innovations that we are seeing in the CPU domain to target faster inference. There's vector units are improving, there's ISA support, and there's all kinds of revolutions happening there inside the CPU. However, we believe that for sustained high performance AI inferencing, there are two key revolutions that will pave the path for the future. Firstly is the hardware revolution to design better interconnects and to bring the CPUs and the GPUs closer. Secondly, the software revolution, where there's a lot of focus on auto-generating high-performance code to avoid hand-tuned low-level kernels. Now, we believe that these revolutions are not just for the CPU, right? But this is taking a more systems view of the entire problem space, making the case for better AI inference overall. That pretty much brings us to the end of the workshop. This is the fifth talk in the workshop. So let me take a couple of slides to recap what we've learned through this workshop and to conclude the workshop before we open for questions. So we went through 5 one-hour-long sessions that was opened by Chris Bhaskar on Monday, where he overviewed the problem space of using AI in manufacturing. Jacob spoke on Tuesday about challenges in adopting ML in manufacturing and gave examples of use cases and algorithms and challenges there. Steve had a beautiful demonstration of some of the examples of how image and data flows in our tools, focusing a little bit more on the infrastructure side. Mark then took it closer to the hardware, where he spoke about how to minimize copy overheads when sharing GPUs on a single box, talking about some of the challenges with data movement, GPU memories, and so on. And finally, today I spoke about running AI inference on the CPU and how vector units can be leveraged and what are the new advancements in the ISA for us to aid inference. So as a conclusion for the workshop, let me highlight some of the points that we'd like you to walk away from these 5 days. Semiconductor manufacturing has been revolutionized by AI and HPC. Now, semiconductors are a very important part of the global economy, and using technology from AI and HPC is enabling us to keep Moore's law alive. It's important to keep Moore's law alive because that's really what has enabled taking a supercomputer from 20 years ago and putting it into your pockets in the form of a phone. So keeping Moore's law alive, our inspection and metrology tools really require these cutting edge technologies to keep that alive. Now, KLA is already leveraging solutions in this space in its products. We have our ESL10 system, which is the industry first manufacturing tool that leverages integrated artificial intelligence with the smart deep learning algorithms that Steve spoke about on Wednesday. It's therefore, in our opinion, a very exciting time to be an engineer at the intersection of AI, HPC, and manufacturing. And consequently, it's a very exciting time to be an engineer at KLA. Thank you very much for attending the talk. Thank you very much for attending the workshop. We are really glad We are very happy to have hosted you through these 5 days. I'll leave you with a few pictures that represent some of the work that we do specifically out of India. The first picture is one of a clean room that's inside our office in India, where some of our engineers got a chance to try their work on a real tool that you can see in the backdrop. The second picture is a conference that we hold in India every 12 to 18 months, where the employees of KLA and some industry delegates actually talk about some of the key technology pieces that happen at KLA, including posters and papers and keynote speeches. And the third picture is where our recently opened office for the AI Advanced Computing Lab has been opened, and that is in the IIT Madras Research Park. Reach out to me or to anyone at KLA for more information. We are actively looking for collaborations with academic partners in this space. You can feel free to write to me. You can find specs of mine here or online. And we are also hiring interns and full-time engineers in the space of AI, HPC, and also in software. You can look up both for KLA India and KLA Worldwide what openings we have, and feel free to apply to there or to write to me about this. Thank you very much for your talk.
Great. Thanks a lot, Pradeep. It was a very informative talk. I would like to ask you some questions in the limited time, but do you have any final thoughts on what you want to convey or something?
I do have one slide that I want to share in the end. Maybe you want to do questions first and then we'll get to that, or do you want me to run that first?
I'll ask you. Yeah, there were a few questions which I thought will be useful. So if you could give a brief highlight of what is AI inference, that was asked by many students, many participants.
Sure, absolutely. Right. So you can back up a second and think about an AI model like something to which you can ask a question and it gives you an answer. The question you ask it can be, give it an image and you ask it, what is the image? You can give it a sentence and you can ask it, translate it from English to French. So inference is the process by which you ask an AI model a question, which is the question. Again, you provide an input, which is the question, and gives you an answer. So inference is the process of asking the question. Now, the prior step to asking the question is you need to make the model ready. That's called training, where you tell the model that here is an example and here is the answer. And the model figures out how to get from that example to the answer. And once it's trained, it's like your brain. Think of it like your brain. When you were a kid, you were given a bunch of pictures of dogs and somebody told you that's a dog, that's not a dog. And you learned it. That's training. And then inference is you see a dog on the road, you say, hey, that's a dog. That's inference.
Great. Thanks. I'm going to skip to this question. What is convolution and what is a convolution layer?
Sure. It's a good question because it's actually philosophical also at some level. So a convolution layer basically is it's an operation by which you take a certain set of pixels or a matrix and you try to apply a filter on the matrix and you summarize the matrix. Let me give you the best way to think of convolution is with an example, right? So let's say that you're only interested in the middlemost value of a 3x3 matrix. So what you basically do is you apply what's called a kernel, which is another 3x3 matrix that just has 1 in the center and zeros everywhere else. And the convolution operation is you take two matrices, same size, you dot product every element by element, and then you sum everything up. So if you take a second kernel that has just 1 in the middle and 0 everywhere else, every other element becomes 0, and the summary that you get is just the middle number. So the different types of kernels help you extract different information about the original matrix. Remember, the matrix typically represents an image. So different filters represent different properties, like you can try to do a low-pass filter, an edge detector, all kinds of fancy detectors. You can detect vertical edges, horizontal edges. So different convolutions have different properties. And a convolution layer basically implements this for a network.
So when you were talking about different instructions, you kept mentioning this term ISA. Some participants wanted to know what that is.
Sure. So ISA stands for Instruction Set Architecture. It is basically the contract that a CPU or a GPU provides to the software, saying that if you give me this instruction with this information, I will do this operation. So it's like a contract, right? So if you have to write program that has to run on the CPU, you have to obey the contract. And so you have to write instructions and give instructions to the CPU that follow that contract. And that contract is the ISA. It's the instructions. You can think of, there is instructions for adding, multiplying, dividing, things like that. Loading, storing.
Sure. Then towards the later part of the talk, you were mentioning something about RISC, and then RISC 5 or something was written. What was that?
So this is a very exciting new development, right? So RISC 5 is a new ISA that has been made popular of late. There's a lot of work around this ISA, right? Basically, RISC stands for Reduced Instruction Set Computer. And the philosophy of the ISA with RISC is that you have few instructions. That's why it's called reduced instruction set. And it's reduced instruction set because each instruction can take a maximum of 2 input operands and produce 1 output operand, as opposed to a CISC instruction set or CISC, which can take more than 2 instructions as input and produce more than 1 operands as output. So that becomes more complicated. So RISC 5 is the 5th generation of the RISC architecture. And there are several RISC 5 ISA implementations that are very popular, including the Shakti processor that has been done by IIT Madras. And there's lots of companies formed around this. There's lots of open source processors. RISC 5 is a very exciting development in the architecture domain right now.
Sure. Thanks a lot, Pradeep. That concludes our question answers. I request Pradeep to now conclude the overall workshop.
Okay, thanks, Rupesh. Again, I really would like to extend a really big thanks to all of those who are involved. Right? So we had really enthusiastic participations. We've received over 28,000 registrations, over 2,500 live participants daily, including today. We had over 2,000 playback of all videos already, and it's been really good. Right? We've had great fun putting the talks together, presenting the talks here, answering all the question and answers. And I apologize if some of the material was either too simple or too detailed to all of you. We tried to address a common audience. Of course, the audience is extremely diverse, so it's very challenging. But I would really like to thank a lot of people across KLA, across IIT Madras, who have enabled us to put on this wonderful show. We had speakers from KLA who really I've bugged them a lot to get me talks and process talks and get all of it together, practice talks, etc. HR team, corporate communications, making sure you guys got all your emails in time with the right links. The telecom team with George and Aaron, who made sure that all the videos are available and that you can see them well. The IT team who enabled me with the webinars, putting everything together. My management, who's basically enabled me to put this together. I've not done too much real work in the last couple of weeks. And IIT Madras, of course, right? Vishal from IIT Madras Reach team, Ricky, who's our resident TA, Rupesh and I have worked with all of you. I really thank you very much. And I sincerely hope that this workshop got you excited about AI, about HPC, and about KLA, right? I hope you continue your journey of learning and that our paths cross at some point. Feel free to reach out for questions, comments, opportunities, whatever else. We'd love to hear from you. Thank you very much for being here. Have a good evening. Rupesh, anything else you want to add?
Yeah, since we have 1 minute, I'll say that I would like to thank the KLA team, Pradeep, for this wonderful set of lectures, the talks, and I'm sure that people will feel enthusiastic about the 3 things that you mentioned: AI, HPC, and KLA. I must say that we had a very, very nice participation by the participants, and we would like to take this forward in some or the other form. Thanks a lot, everyone.
Thank you. Have a good evening. Good night.